The second application of the Taylor theorem that we're discussing today is to prove inequality. That is, we compare the function f of x with its associated Taylor polynomial Pn of x once you know the sign of the remainder term. Here is an example. Let f of x be the function cosine of x. We would like to compare 1 minus 1 half x squared with cosine of x. We choose x0 equal 0 and equal 2. Then first step is to construct the Taylor polynomial. And to do that, we have to compute the derivatives of the function. The first derivative is equal to minus sine of x. When we evaluate 0, that is minus sine 0 equal to 0. The second derivative is minus cosine x. When we evaluate 0, it is minus cosine 0, which is minus 1. And the third derivative is equal to sine x. So we can write out the Taylor polynomial of degree 2, which is 1 plus 0 times x minus 1 half x squared, which is 1 minus 1 half x squared. To compare the function with Taylor polynomial, we need to analyze the error term, which is the third derivative evaluated at some point c divided by 3 factorial multiplies with x minus 0 to the 3, which reduced to sine of c divided by 3 factorial times x to the cube. Now we consider different cases. So here, the first case is that x is within the interval from 0 to pi. In this case, we have 0 smaller than c smaller than equal to x smaller than equal to pi. Therefore, sine c is greater than 0. X to the cube is also greater than 0. So the error here is greater than 0. Yes, cosine x is greater than 1 minus 1 half x squared. And we argue similarly in other cases. So the second case is when x is bigger than pi. The third case is when x between minus pi to 0. And the fourth case is when x smaller than minus pi. In all cases, we arrive at the same conclusion, which is 1 minus 1 half x squared is smaller than cosine x. That's why this inequality is true for every real number x. So that is an example of how the Taylor theorem can be useful to prove some inequality. Last but not least, another application of the Taylor theorem is to determine relative extrema. So this is a generalization of the first relative test we discussed earlier when mentioning application of the mean value theorem. Remember, the Taylor theorem is a generalization of the mean value theorem. That's why it gives another generalization of that first relative test to determine relative extrema. So here is the theorem. Let I be an interval and x0 be an interior point inside I and n greater than equal to 2. Suppose that f prime, f double prime, dot 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 up to the n derivative of the function f exists and are continuous in a neighborhood of some point h0. And furthermore, the evaluation of all these derivatives from the first derivative to the n minus 1 derivative of the function of this point f0 is equal to 0. But the n derivative is not equal to 0. If n is even and the n derivative here is greater than 0, then f0 is a relative maximum. If n is even and the inequality is reversed, that is, the n derivative of the function f evaluated at f0 is negative, then f0 is a relative minimum. If n is odd, then f has neither a relative maximum or minimum at f0. So you can see clearly this is the generalization of the first derivative test. For the first derivative test, we only consider the first derivative. And here we consider the evaluation of the n derivative of the function. So here is an example. Let f of x be x to the cube plus 2, x0 equals 0. Now we compute its derivative. The first derivative equal to 3x squared. The second derivative equal to 6x, and the third derivative equal to 6. At x0 equals 0, we evaluate f prime equals 0, f double prime equals 0, and f triple prime equals 6. In this case, n equals 3, which is odd. So the point h0 equals 0 is neither a relative maximum or relative minimum.